Okay, so ready to start for the afternoon session? It's me on. It's me. Why on the MPL aspect of things? Why we're interested in exfoliation? The view that we're coming to with regards to our own work, what we've been doing, and what we'd like to do going forwards. Reiterates a little bit what I said this morning, but it's scene setting. It shows our heritage, if you like, in measurement. So we're formed again back in the beginning of the 1900s. We're a government-funded research laboratory doing work into how to improve measurement techniques and to make measurements better. Over the years, we've done a lot of work solving measurement problems for industry and in conjunction with industry. Providing both support for heavy industry, health, security. We're the UK's National Measurement Institute, and so provide UK industry and services with consultancy services, and what we like to do through our knowledge transfer is to apply our measurement techniques and understanding to problems and to help solve those problems, perform better measurements that perhaps standard test houses aren't in a position to do. There's this quote that gets banded out at every corporate kind of presentation. When you can measure what you're speaking about and express it in terms of numbers, that's when you truly understand it. And if you can't express it in terms of numbers, then your knowledge is somewhat lacking. So that's really at the heart of what we're doing here at MPL. Now, if we're turning to exfoliation and power generation, we're all aware over the last 10-15 years there's been an increased awareness of carbon emissions, the need for higher efficiency, fossil plant. You've got this graph showing how with increasing plant efficiency you can have a reduction in the CO2 emissions. And there's a number of ways that you guys in industry are approaching this. This two-pronged attach is often talked about, where you can increase the efficiency by raising the temperatures and pressures, using biomass, but also do carbon capture and storage, which has the unfortunate hit on the efficiency, so you need to take both approaches. So doing that, you're invariably increasing the harshness of the environments you're expecting these materials to perform in. So conventional materials that have been used over the years are being pushed to their limits. So you either use a new material or you change the system, so maybe apply a coating. And to do that, you need reliable and accurate characterization of the performance of that material or that system. That's where our interest really lies. So we're interested in improving the test methods, improving the testing facilities, so that we can better reproduce the kind of conditions you see in service, try to better reproduce the morphologies of the oxide scales that are formed, to increase the confidence in laboratory data, which is easier and faster to produce than, say, doing a steam loop in a power plant. It's more controlled too. Now, within materials, the materials division as a whole, there's generally three main themes. That's processing, performance, and the characterization. If we take out materials and put in exfoliation, the same applies really. You've got the processing, so you've got considerations of the alloy composition, optimization of the alloying additions, the implication that that has on mechanical strength, creep strength. You've got surface modifications, and we're here in some of the breakout sessions about how shot peening has been used to modify the surfaces, how coatings can be used to modify the surfaces. microstructural control, the use of coatings. In terms of the performance, there's the oxidation kinetics, so how fast something oxidizes, how well the scale adheres as it grows, how strong the oxide is, what is the critical thickness at which exfoliation will occur for different systems. And also the thermal properties, so as the oxide grows, how does that impact on the heat transfer through the oxide, through your superheater, and how does that change with time as the microstructure changes, as the morphology of the scale changes, as you get these voids forming, you may get lift off of the scale, blisters, all that will affect the heat transfer properties. Characterisation of the material. One thing that we've been working on over the years is the effect of the testing parameters. So we do laboratory tests. What we've looked at over a number of programs is the effect of different experimental parameters, what that has on the oxidation kinetics and sporulation characteristics of the materials we look at. These started off as isothermal exposures, but over the years we've moved into looking at thermal cycling. So that's been shown to better reproduce the kinds of morphologies that Barry was showing earlier. Over recent years, we've included heat flux, moving away from a purely isothermal type condition that had some kind of temperature difference over the wall of the sample. We've also looked at models, so oxide growth models, how the strain develops within the oxide scales, how that relaxes with thermal transients, the effect of creep on that, and the cracking both through thickness and interlaminar of the oxide. This is just a schematic. I think it's something we all know and understand. As you start with a bare unoxidized cupin, you expose that for some temperature for some time in an atmosphere, whether it be a mixture of argon steam, pure steam, or just air oxidation. The oxide forms and thickens. We have some kind of cooling cycle, a temperature transient. Depending on the cooling rate, you get stresses developing within the oxide between the layers. Oxide cracking can occur, and then finally you get the debonding and sporulation. So that kind of mechanism has been at the heart of how we've been approaching the modelling of sporulation within NPL. This slide was just really aimed to show how sporulation isn't a simple phenomena to try to understand. Depending on where you are in the plant, what your temperature conditions are, what your operating conditions are, you can get different types of sporulation occurring from different materials. So you can get repeated sporulation from individual spots. You can get large sporulation happening once, or light sporulation over the whole surface. So that was just really just to flag up the different types you could get. And so when we're trying to model that, we need to try to identify exactly what we're trying to reproduce with our models. Is there a critical spacing between the oxide cracking, which results in either large flakes of oxide or smaller flakes of oxide? These are the kind of things that, in the back of my mind, we need to think about in the upcoming sessions, maybe with the breakout for the modelling session. In terms of the impact of exfoliation, well, again, we've heard that this morning really with John's examples, with the solid particle erosion, the thinning of the oxide of the metal walls. What we get is obviously with the oxide coming away, you use up the metal, so you get metal wastage. You can get localized increase in the strain through thinning of the tube. You get changes in the thermal properties. So to illustrate this, it's just a like to use. So if we consider a 9 chrome steel at 600, it doesn't take too long to grow 100 microns of oxide. Ian can correct me if I'm wrong, but that would give you about a 10-degree temperature rise. It takes about 2 degrees for every 25 microns or something like that. So when we then think about the 100,000 hour pre-rupture strength for that, then if we have an increase in the localized temperature by 10 degrees, you're effectively decreasing the pre-rupture strength by 10% on this diagram. So the impact is significant. We've also got the potential for tube blockages, as we've seen previously. So to be able to understand exfoliation, to be able to quantify it, put a number to it, is what we would like to do. And to do that, we need to understand the oxidation kinetics. We need to understand them as a function of temperature, pressure, heat flux, and geometry. It would be nice if between laboratories we could agree on a number. Heat transfer. We need to understand the heat transfer through the oxides if we're going to model the sporulation. It's obviously a key parameter. Not only will it affect how the oxide continues to grow with the insulating effect and have a rise in temperature. So that's also key to understand. And also the strain development, not only the development of it, but the translation between the different layers, the effect of voids, how that affects the whole continuum. Made reference to being able to agree on the oxidation kinetics. This was a round robin that was reported in 2002, so around the time of the last workshop. It was on P92, 1,000-hour exposure, a couple of temperatures there, 600 and 650. Some of the laboratories were using atmospheric pressures, some elevated pressures. This shows the oxide thickness measured across those laboratories, and there's significant differences between the participants. We did a round robin a few years ago as part of a UK-US collaborative program. This shows results from 3 laboratories. It's the same batch of material, again, P92. Yes. Now, 2 of these laboratories were doing it at atmospheric pressure. 1 was slightly elevated. This shows the specific mass change in this case, but again, we got fairly significant scatter between the 3 laboratories. So, which value do you use? Now, interestingly enough, once you discount the initial oxidation period, you could pretty much overlay the rates of those 3 labs over each other. So, it seems to be the initial 1,000 hours that seems to be one of the critical things that we should perhaps concentrate down on. We need to also think about what we're measuring. This is some early data from some high pressure work we've been doing. So there's not many data points to pull conclusions from or anything, but it gives an indication of an effect. So what we have here is the specific mass change on the top graph, oxide thickness on the bottom one, for T23 at ambient and 50 bar, flowing steam in both cases. And we also got grade 92 atmospheric, 25 and 50 bar. So if we look at the specific mass change and measure purely just the specific mass change of those samples, then we see that in both cases for the T23 and grade 92 material, we have an increase in the mass change with pressure, leading you to theorize that increasing pressure would increase the oxidation kinetics. If we just measured the oxide thickness, or indeed the metal loss, then we get the inverse result, where we have a thinner oxide forming on those alloys with respect to pressure. first section, this is for the grade 92, it's 1,000 hours at 650 degrees C. We've got the atmospheric pressure here, and this is at 50 bar. So what we're seeing is a densification of the oxide. So again, it's something to be aware of when you're doing your measurements. If you use one method over the other, you might be missing something. In the past, we've looked at the effect of heat flux as well on the oxidation kinetics and the morphology of the oxides grown. These are results for 15MO3. We did some isothermal exposures on cubans. They were 10 by 10 by 3. And we also did some heat flux exposures where we suspended a tube in a creep frame furnace, and we took two approaches. The simpler one, which is this data here, was to just blow compressed air through the middle of the tube. And we got about a 50-degree temperature difference between the outside of the tube and the inside of the tube. We had thermocouples welded along the length. Plotted here the mean scale thickness with respects to exposure time, and compared that with the isothermal data points, and we're getting a thicker oxide forming under those heat flux conditions for the three temperature ranges there. We basically cut samples out of different areas of the tube so that we could get 450, 475 and 500 degrees C. We repeated that with T23. Sorry, if I go back to this, one of the comments we had at the time was this truly a heat flux effect, or was it a geometry effect? We were using a tube and comparing it to a flat cube. So what we did, we cut a section of tube, and we exposed that isothermally as well, and that gave similar oxide thicknesses as the flat cube. So fairly confident that it is a heat flux effect rather than anything caused by the geometry of the tube. What we saw in this one too, which I haven't shown in this presentation, was the morphology of the scale was different under heat flux conditions to the isothermal. We saw in the oxide was we had alternating layers of fine grain material, thick grain, coarse grain material, and that alternated as we went through the layer structure in the scale. What we wanted to do then was to see how a different alloy would compare. So we obtained some service exposed material from E.ON. We looked at that under the microscope using EVSD, and again we saw this structured multi-layered oxide that Barry was speaking about. We did a similar kind of heat flux exposure on tubes of the T23, and whilst we still saw an increase in the oxidation rate with heat flux, in this case it was steam cooled, so we actually started pumping in steam through the internal of the tube rather than just compressed air. We didn't actually reproduce this layered structure or the same structure as we saw in 15MO3.
Short question, can I ask?
Yeah, fire away.
Did you measure the temperatures inside the tube or close to the oxide?
On the 15MO3 samples, we had the thermocouples welded on the outside of the tube and on the inside of the tube at the same position. So we had corresponding measurements inside and outside. That was with the air-blown samples, so the ends of the tubes were open. And with the T23 samples, because we were cooling with steam, we had welded ends on the tube. So we didn't have the same opportunity to have thermocouples welded on the inside. So what we did in that case was we had a second tube running through the work tube, which had the thermocouple in, so we were measuring the internal steam temperature, if you like, rather than the wall temperature. We've also done some work on heat transfer. Again, this goes back a few years now. This was in 2007. This is using the laser flash technique. So you have a small sample sits here. You fire a pulse of laser at the bottom of the sample. You measure the temperature rise on the other side of the disc. What we did was we did a number of measurements, and through those measurements we developed a model for the heat transfer as a function of oxide thickness. So early on, 20 micron oxide thickness, that gives you the temperature rise with time. You just see how the gradient changes once you've got 200 microns of oxide on there. And we, from those graphs, we calculated thermal conductivity from the scale as a function of time and thickness. These were transient measurements though. What we'd like to do is to make steady state measurements, and there's some proposals internally within the thermal group to develop the apparatus to be able to do that, both on steam grown oxides and also fireside corrosion products. Whether it gets funding or not. Okay, this is possibly a contentious one, but coefficients of thermal expansion. My understanding, this is what drives the delamination and the exfoliation. And over the years, many people have used this data, the ARMIT data. It was brought to our attention a while back, this around 2004 I guess. There was other data that had been published that didn't agree with the ARMIT data, so which one was right? So within one of our programs we had a bit of time, so we did some measurements. This is just comparing the coefficient of thermal expansion with temperature for the data in the EPRI report and Levy's data. So it doesn't show this large hump. So we said, yeah, okay, we'll have a go. We'll see what we can measure. From Les Buchanan, I obtained a sample of spoiled oxide. We also made up some sticks of consolidated hematite from powder, and we did some measurements on those three samples. So the boiler scale is this line here. That compares well with what was Levy's run 2, where he didn't have any oxidation occurring during these measurements. The air-fired ferrite is this dark blue line, and this is the reduction-fired ferrite. I can't remember why the measurement stops there. It may be that the sample crumbled in the rig. If we plot that data then in terms of the mean expansion coefficient, we have fairly good agreement between the boiler scale and Levy run 2 still, and this seems to be agreeing with the Levy data for the reduction fired ferrite. The measurement was cut short. We didn't get the same kind of rise up as the ARMIT data showed in the EPRI report.
There's a suspicion of homelessness.
Yes. So all I can say is the work we've done here tends to side on the Levy data rather than the yes.
We will report shortly, maybe this year, we got some measurements of thermal expansion of magnetite using neutron diffraction.
Okay.
The data is being post-processed now.
Yes.
We have to see how that will go.
Oh, you're going to leave us hanging. Oh. Okay, it'd be interesting to see what you get when you've had a chance to process it all. But again, this subject is something that's going to come up in the breakout sessions. So it'll be interesting to get other people's take on it, and I think we still need to do more work there to try and bottom it out. Yeah. I mean, we get a small hump, but nothing as marked. Okay, so to finish up then, NPL's view on it is what we'd like to achieve is characterization of the performance through measurement, improved measurement. We know that exfoliation has a major effect on plant life and operation. How failures within the US, we heard of the failures within Denmark. Doesn't seem to be so many in the UK. Maybe that's something that the utilities group can address maybe and see why that is. Higher operating conditions, it's going to get harsher, things are going to get harder for these materials. Can we expect more of the same? These new materials, these new systems, are going to need characterization. They're untried, they may be new alloys, they may be alloys that are being used in a different part of the plant under different conditions. So what we need is repeatable and comparable tests to give confidence in the use, to the modelling of these alloys, such that you can have confidence in your plant asset management. And obviously we want a nice safety record. What I'd like to do is to improve the laboratory testing techniques such that they better represent what you see in service, so that we can apply what we do in the laboratory to what you see when you do your measurements on plant. Maybe not reproduce it entirely, but if we can get some kind of correlation so that if you see one type of failure or microstructure in the lab, that might relate to such a condition in service. And clearly, there's a lot of work on modelling. Improved models is something that we're keen to continue exploring. Okay, if there's any questions,